Hello, welcome back. I'm Jason. Now, truthfully, I have always been absolutely fascinated by the Voyager spacecraft. Something about our collective selves, meaning humanity as a whole, sending out a creation of humanity, the space probe, sending it out to the stars. Now, space, as you know, is big. Now, when I say big, I mean really, really big. No matter how big you can imagine the space between the stars, it is much, much, much bigger than that. Nobody can imagine how big our galaxy is, much less our universe. So it'll take the Voyager space probes that humanity has sent out toward the stars literally thousands of years to get anywhere near a close approach to another star. But still, what's amazing about this, to me anyway, is that humanity is very hopeful. So we put a message on a spacecraft that departed the Earth decades ago, a message to any being or any alien that might be out there, anyone who might find it, even millions of years from now. And this personally gives me comfort that even after I'm gone personally, or even after all humans are gone, everybody on the planet, out there somewhere is a message that we wrote saying quite literally hello to anybody or any alien out there who might find it. And this is what I want to talk about today. What would happen if aliens ever actually do find the Voyager spacecraft and our little message in a bottle, so to speak, to the stars? So imagine, if you will, for a moment, that you're a part of an alien crew somewhere on a spacecraft in a distant part of our galaxy. So your long-range sensors detect it first, right? A tiny artificial object drifting through the vast emptiness between the stars. Quite literally inky blackness between these enormous things that we call stars. And as your craft approaches this object, it appears unlike anything in the database of known space phenomena. It's a metal construct, clearly built by intelligent beings, but from where? From how far away and how long ago? As you study this strange object, its most prominent feature that you can see from the outside anyway, was a large dish-shaped antenna that was pointing back in the direction that it presumably actually came from. Now, extending from its hexagonal body was an impossibly long boom. Not impossibly long literally, but quite long in comparison to the bulk shape of the spacecraft. And at the end of that boom, carried what appeared to be scientific instruments. Now, two cylinders containing some kind of a power source protruded from the side of this craft. But the most intriguing thing of all about the whole thing was a golden disc, carefully protected, clearly meant to be found right on the side of the spacecraft, clearly in view. What is that? So the bulk of what I want to talk about today is this golden record bolted to the side of the Voyager spacecraft. It's fascinated me forever. But the question is, could the golden record actually be decoded by an alien civilization? How would an alien civilization even know how to do that if we built it on Earth and they don't have our technology? How would they know that the information is encoded on microscopic scratches on the record, literally scratches on the surface of this record? And how would the encoding actually work? Now, the humans that built this craft put a clever message which was engraved on the outside surface of the record, sort of like instructions or some sort of instruction manual. And for a bit here, I'd like to talk for a little bit to exactly what this message to the aliens actually says. But before I get to that, and believe me, it's absolutely fascinating what we put as a message on the outside of the spacecraft, I like to go back to the beginning, when these two little spacecraft built by tiny little humans set out on their long journey. So the year was 1977. Humanity launched two of the most ambitious missions in the history of space exploration. Voyager 1 and Voyager 2 were spacecraft that began their grand tour, so to speak, of the outer solar system, carrying with them a message from Earth. Now, the message itself was a golden record, as we've been talking about, on the outside of the spacecraft. Now, there's a picture there explaining how to read the record, and on the inside contained messages, sounds, musics, and images from all around the world. Now, Voyager 2 was actually launched first, and it was launched on August 20th, 1977. And that was followed by Voyager 1, which was launched on September 5th. Now, even though Voyager 1 launched second, it actually took a faster trajectory, and that made it the most distant human-made object in space. Both spacecraft actually use what's called a gravity assist, and I'm going to talk about that in a second, from Jupiter to Saturn to gain speed, with Voyager 2 actually continuing on to Uranus and Neptune. So while Voyager 1 actually just hit Jupiter, Saturn, Voyager 2 hit Jupiter, Saturn, Uranus, and Neptune before both of them leaving the solar system. Now, this trip itself, this grand tour of the outer planets, was only possible because of the very rare alignment of the four outer gas giants, Jupiter, Saturn, Uranus, Neptune. This doesn't happen very often. The relative positions of these planets are always changing as all the planets orbit the sun, and because the planets that orbit closer to the sun move through space faster, they're very rarely actually lined up like this. So it was quite lucky when NASA's mission planners discovered a rare astronomical alignment that would make this ambitious mission possible, and they got the funding to make it happen. So it turns out that about once every 175 years, the outer four gas giants of our solar system align in a way that allows a spacecraft to use their gravitational fields sort of like a cosmic slingshot to gain speed to exit the gravity well of the sun and exit the solar system, so to speak. This is what we call the Grand Tour alignment, so to speak, and it last occurred in the late 1970s, making the Voyager missions possible in the first place. If we, for whatever reason, missed this window of alignment, we would have had to wait until somewhere in the 2150s for another alignment opportunity. Now, this rare alignment allowed both spacecrafts to perform a series of gravity assists. It used the planet's gravitational field to gain speed without using any extra fuel. Now, just to give you an idea of the numbers here, Voyager 1 increased its velocity by somewhere around 35,700 miles per hour through these gravity assist maneuvers, while Voyager 2 achieved the only complete grand tour of the outer planets in history. It's never been done before, and it's never been done since, because that spacecraft, as I mentioned, hit Jupiter, Saturn, Uranus, and Neptune, and that was only possible because of the alignment and the gravity assist. I want to talk for a second about these gravity assists, right? So what you have is a planet here, and at first it doesn't really make sense. If you're a spacecraft, my finger, and it's approaching, it's being pulled faster and faster and faster as it approaches the planet, and then it doesn't quite hit the planet, it goes next to it, and then it goes to the other side. So it's gaining speed here. You would think that as it goes on the other side, that it's the gravity slowing it down on the other side. So you don't think you really gain any net velocity. That took me a long, long time to actually figure out the answer to this. How is it possible when a spacecraft is attracted, it speeds up, and then it should slow down on the other side by the same amount? So how is it doing anything? Well, the reason is because the planets are moving around the sun, and they're moving very, very fast around the sun. So what's really going on is you can imagine the Earth moving, and then it's drawing it in, and then as it passes on the other side, the Earth's gravity well is moving along with the Earth. Think of it that way. And as it's being sucked in, it's not just a stationary thing. You can think of it as almost like a ball coming this way, and then I use my hand to like if this were a ball, I use my hand to like push it as it moves past. So it's not that it's just moving past a stationary object. The Earth is moving, and it's giving some momentum to the spacecraft as it flies by because the Earth is moving as well, and the gravity well is kind of grabbing the probe and throwing it as it moves past. That's why we call it a slingshot maneuver. Now, we can go on forever talking about the engineering behind the space probe, right? But I'll just give you one fact that hopefully will blow your mind, right? We're talking to this spacecraft all the way outside the solar system. Even today, even at 2024, when I'm recording this video, we're still in contact with the spacecraft, right? But Because we're so far away, the radio waves traveling to and from the Earth are very, very weak. And so when Voyager transmits, it does have a dish, but the waves still spread out somewhat as they travel towards the Earth. So when the radio waves from Voyager reach the Earth, they are a billionth of a watt of energy is what's actually intercepted on the surface of the Earth. So it's quite amazing that we can actually talk to them at all. Think about a billionth of a single watt. I'll give you one little number that was true maybe 10 years ago when I read about it when the Voyagers were a little bit closer. So it's a little bit out of date, but it's pretty close. That is equivalent to the amount of energy that you might see if you take a single Christmas light, which is on your Christmas tree, and flash it on and off for about 1,000th of a second. That is incredible low energy that's being transmitted from this probe to Earth, and it's quite amazing that we can hear it at all. And that's why we have these enormous antennas and these enormous arrays of antennas on the Earth arranged on the ground to be able to listen for these incredible weak signals. Now today, both space probes continue their journey into interstellar space. Voyager 1 is actually headed toward the constellation Ophiuchus, and it will pass within about 1.6 light years of the star AC 793888 if you're keeping track of it, and it'll do that close approach in about 40,000 years, so pretty far in the future. Now Voyager 2 is actually traveling toward a constellation called Telescopium, and it'll pass roughly about 1.7 light years at closest approach to a star named Ross 248 if you're keeping score, in approximately, again, 40,000 years. Now it's easy just to mow past these numbers and not care, but you know, we're in a solar system here, and we know that the nearest star to us, Proxima Centauri, is about 4 light years away. 4 light years away. And that means that even at the speed of light, incredibly fast, right, it would take 4 years for us to actually reach Proxima Centauri, and that's why we can't do it now, and that's why we probably won't do it anytime soon. These spacecraft are headed about 1.6, 1.7 light years closest approach to the stars that they're roughly headed towards. Right? So think about it. The distance from here to Proxima Centauri is 4 light years. So about halfway there, that would be the closest approach. If you were actually an alien on a planet orbiting one of those stars, the odds are you would never know that that spacecraft was sailing right by you because, you know, it's going to be dead by then. It's not going to be transmitting anything. It's going to be completely dark. It's not like it's lit up like with a fusion reactor or anything. And it's literally passing almost 2 light years away, half the distance to Proxima Centauri. So the distances involved here are mind-boggling, and that's why I said, no matter how big you think space is, it's way, way bigger than that. Now for me personally, it's also impossible for me to actually visualize 40,000 years. I just can't even think of it. But let's try to put it in perspective. 40,000 years ago, our ancestors were actually in the midst of an upper Paleolithic period, or the late Stone Age is probably a better word for it that you might have heard before. Modern humans had just begun their final migration out of Africa, spreading across Europe and Asia. Now this was the dawn of human artistic expressions. So we know in caves, which are France, Indonesia, and other locations around the globe, our ancestors were creating the first known cave paintings around this time. Beautiful renderings of lions and mammoths and rhinos and other animals, and they were fashioning the first musical instruments. Which, fun fact, the first musical instruments fashioned were flutes, which were actually carved from bird bones and mammoth ivory, creating melodies that echoed through the Ice Age valleys way back then. So the question to you is, where will humanity be in 40,000 years from now? It's impossible for me to contemplate. All right, that was a little detour through time and space, as we now know the Voyagers, where they're going, where the close approach will be, and how far away in the future it'll be. But let's now return to the Voyager craft itself, as our alien friends have now discovered it drifting in deep space. Now, if an alien ever finds this, I think they'll be fascinated by it, because the Voyager spacecraft, for the technology of the day, are actual technical marvels, right? Each one of these space probes is about 3.7 meters tall and has a mass of somewhere around 825 kilograms. That's about the size of a small car, with very large booms protruding from the central structure. Now, the most prominent feature that you would notice right away if you're an alien that's intercepting this is what we call the high gain antenna. This is a 3.7 meter wide dish that maintains communications with the Earth. Now, a 13-meter magnetometer boom extends from the body, carrying instruments to measure magnetic fields in space. Now, the dish will be pretty obvious to anybody finding this that was for communications, because you need that shape in order to channel the radio waves and get a tight beam to Earth. But I mentioned the power, even though it's in a tight beam, it's still spreading. And so we actually intercept very, very, very a few fractions, billionth of a watt from the spacecraft. Now, these long booms are actually in place because we're trying to measure the magnetic field way out in the deep solar system. You know, the sun has a magnetic field just like the Earth has a magnetic field, although it's much, much stronger. And so what we really want to do is we want to figure out where is the end of our solar system, for lack of a better word. Where does the magnetic field of the sun get so weak, way beyond Pluto, that the magnetic fields of the other stars, like Proxima Centauri and other stars nearby, we can actually start to measure their influence. That's a good boundary for where the solar system's influence sort of ends. Now, what you want to do when you measure magnetic fields is you want to put the sensors on a long boom far away from the central part of your spaceship, because all the computers, anything electronic is going to produce magnetic fields from electricity moving around. And so you don't want to measure that. So they had to build a very long boom to put the magnetometers to measure the magnetic fields far away from the spacecraft. And that's why they're out there. Now, this boundary between the end of the sun's influence for the magnetic field dropping off and the beginning of the influence of the other stars is called the heliopause, helio meaning sun. And they just found it recently, actually. They've been waiting and waiting and waiting way past Neptune here. Recently, we found the heliopause at about 120 AUs, 120 astronomical units. Remember, an astronomical unit, 1 AU, is about the distance from the Earth to the Sun. That's about 93 million miles. So 1 AU is about 1 Earth orbit radii. Now, FYI, the orbit of Pluto is about 36 AU from the Sun, but the heliopause was found to be about 120 AU. So if I remember correctly, they had to wait a lot longer than they actually thought, and they were worried that the spacecraft would run out of power and just wouldn't function anymore before we found it. But we finally found clear evidence of the heliopause, where the magnetic field of the Sun is coming down in such a way that the influence of the magnetic field of the adjacent stars is coming up in relative equality there. And so that's called the heliopause. We just found it recently. Now, each of these Voyager spacecraft is powered by three radioisotope thermoelectric generators. Say that 3 times fast. Radioisotope thermoelectric generators. RTGs is what they're called for short. They're really remarkable little devices that convert heat directly into electricity with no moving parts at all. No turbines, no generators of any kind like this. So inside of each of these RTGs are actually 24 spheres of plutonium-238 dioxide. Each is about the size of a golf ball, which is protected within layers of iridium and graphite. Now, as you might have guessed, plutonium-238 is naturally radioactive and it decays over time, and it releases heat energy. Now, when the spacecraft was launched, each of these RTGs with the plutonium inside was generating something on the order of 2,400 watts as heat from the radioactive decay. Now, that was enough to warm several small rooms, right? But the real magic happens because that heat has to be converted to electricity, and that happens with a little doodad called a thermoelectric converter, and that surrounds the plutonium. That's what actually turns it into electricity. It's quite fascinating how these work. These converters actually contain thousands of specialized metal thermocouples. Notice the word thermo meaning heat in there. So one end of the thermocouple is kept hot by the plutonium. It's always decaying and it's always generating heat from the radioactive decay. So one end is kept hot, but the other end of the thermocouple is kept cool by the darkness of space, right? Because space is cold, so that's on the outside. Now, this temperature difference or temperature gradient physically causes electrons to flow from the hot end of this thermocouple to the cold end, and that generates electricity. So this is a phenomenon known as the Seebeck effect, and this is why these things are so resilient over long long periods of time because there's no rotating motor like we would have on Earth for generating electricity here. In this case, it's literally no moving parts, and the radioactive decay generating heat physically pushes the electrons in the circuit with no other moving parts. Now, when launched, these RTGs produced about 470 watts of electrical power, which is about the same as 5 really bright incandescent light bulbs. Now, you might say 470 watts, that's less than the 2,000 whatever watts he said a second ago. Well, that's because nothing is ever 100% efficient. So you have the radioactive decay generating heat, right? But then you have to convert that to electricity, so you're getting less watts or less power out in electrical form because of losses there in the conversion process. Now, this plutonium-238 has a half-life, a radioactive half-life, of about 88 years. And the power output has been steadily declining because why? As it decays, there's less of the plutonium left, so it's generating less heat over time. Now, by 2023, each Voyager was operating on less than 200 watts. That's barely enough power to power a few bright LED light bulbs. Yet, even this tiny amount of power is enough to keep the basic systems running in the efficiency and the darkness of space. You might be wondering when these spacecraft will actually go dark and really not have enough power at all. Well, the electrical output, of course, is decreasing over time. They'll continue generating some amount of power until somewhere in 2025, when the spacecraft will no longer be able to operate any scientific instruments. Then, in my opinion, it's a little sad because the Voyagers will truly go dark and silent, a true derelict drifting in space. Now, if you're aliens and you find this thing, you're noticing a dish, you're noticing the booms, and you're noticing the power source, and then you notice that there's these cameras and that they're mounted on a scan platform that can rotate and pivot. And what that does is it allows the operators to track targets as the spacecraft flies past. So each of the Voyagers carry 3 computers to control everything with just 69 kilobytes of memory, kilobytes, and that's less than a typical email contains today. Yet these computers have controlled the spacecraft flawlessly for over 45 years. Let's just talk about this for a second. Kilobytes, that's thousands of bytes, right? I remember when I got my first computer, I was super excited because the hard drive had 20 megabytes, millions of bytes, right? A picture that you might send somebody might be a megabyte nowadays. A movie that you might send somebody might be 2 or 3, 4 gigabytes, right? Billions of bytes. Kilobytes is controlling the entire system, but when you develop it efficiently and you know exactly what you're doing, you don't need a lot of overhead. So they were very smart people designing the spacecraft. The second thing is, you know, I always thought when these spacecraft went out to Jupiter, Saturn, that they kind of like orbited Jupiter and Saturn, but actually the Voyagers were on what we call a flyby trajectory. They couldn't stop. They couldn't like slow down and stop and snap a picture. They took all of those pictures as they were screaming past at thousands of miles an hour. It just doesn't look like they're moving because the planets are so big, but they're screaming by at thousands of miles an hour. And so the cameras, if you didn't do any adjustment, everything would be blurry. How do you handle that? Well, the cameras were on platforms, and the platforms can move and gimbal. So as the spacecraft flew past the planet, the cameras were constantly tracking the planet, somewhat like my fingers are trying to do like this. And so that exposure was kind of like soaking into the primitive imaging systems that they had at the time. But by moving the camera, it had to be perfect, or else everything would be totally blurry. Just another example of how these things were engineered amazingly. Now here is what I get excited about. Perhaps the most fascinating component of the whole thing is the golden record which were on these Voyager spacecraft. They were mounted on the side of each spacecraft. It was a 12-inch gold-plated copper disc, and it was protected by an aluminum case. Now the cover of the case is etched with instructions which were meant to be understood by any technological civilization that might find it. And as you might imagine, the people that came up with exactly how to write instructions, I mean, you can't write them in words, you have to write them in pictures somehow. How do you go about explaining how to read this thing to people that don't, maybe not even have eyes the same way that we have eyes, and certainly don't speak languages the same way that we do? So what I'd like to do first is give a basic overview of the cover of the golden record. But then after we give an overview and you know what's on there, I want to go piece by piece and explain each little bit in detail. I think that's a much better way to tackle it. So here begins our overview of the outside of the Voyager golden record. Now first I want to turn your attention to the lower right-hand corner. It's a diagram showing the hyperfine clarifying transition of hydrogen, which is the most abundant element in the universe. Now, this provides a universal time standard that any advanced civilization should recognize. I mean, they had to pick some kind of time standard because you have a rotating record here and they have to explain it. So hydrogen being most abundant was a good place to start. Now, below that image are binary numbers that establish units of time and units of length, which are going to be used to decode the disk. Continuing our overview, let's look in the upper left-hand corner. This shows how to play the record. It indicates that the correct rotation speed is 16 2/3 revolutions per minute. The drawing on the right-hand side demonstrates how to convert these analog waves, which are on the record, back into images using the included calibration circle that's also drawn on the surface of the record. Now, the bottom half of the cover is actually, in my opinion, the most fascinating part of it because it shows the Earth's position in our solar system relative to 14 pulsars. Now, pulsars are cosmic lighthouses. They're basically rapidly spinning neutron stars, and because they're rapidly spinning, they look like flashes of electromagnetic radiation from the Earth, right? And they serve as galactic landmarks. Any alien would know where these pulsars were. So these are 14 pulsars showing location of the Earth, and there's a 15th line that shows the center of our galaxy, relatively speaking. So this pulsar map could actually allow aliens to determine when and where the spacecraft actually launched from. Now let's get to the good stuff. Inside on this record, if they could decode it, contains the following: 115 analog encoded images. There are also, in addition to the images, greetings, spoken greetings, in 55 human languages, 12 minutes of natural Earth sounds, and 90 minutes of music from around the world, all different genres and all different time periods. Now, the images begin with basic mathematical and scientific concepts, gradually building up to pictures of human life and human culture. What's fascinating is that in addition to all of this, we also included the sounds of waves breaking on a shore on Earth, wind howling through trees, thunder, and also many, many animal calls. There are also heartbeats, there's laughter, and there's footsteps. And the music ranges from Bach and Beethoven all the way to Singalese percussion and Australian Aboriginal songs, really trying to capture the totality of the human experience. Now, the pictures show human anatomy, DNA structure, and scenes from daily life around the planet. Things like people eating, people working, people learning and celebrating. And there are also images of our architecture and our technology and our natural world. Now, this was and is our message to the stars, and I want you to take just a moment, maybe pause the video and think about that. That no matter when you get old and you're not here anymore, and the people behind you, maybe even if the whole planet doesn't make it, I hope that's not true, but even if it doesn't, we have a message out there that's saying, hey, we were here. This is where we came from. Here is a map. And here are pictures of who we were and sounds of who we were, including joy of laughter and the tears of crying and the birth of babies and the wind through the trees and our most beautiful creations like art and music and also mathematics and other things. And even if maybe we hopefully can settle a new planet as maybe our planet becomes uninhabitable, if the sun gets too large, gets too hot here, who knows? Who knows where humanity will end up? But even if we, for some reason, don't conquer the stars, at least we have one emissary of who we were and where we lived. And now what I'd like to do is I'd like to dive into the cover of the Voyager Golden Record and give you a little more detail into exactly what was actually put on the cover. Now, in the lower right-hand corner, we have this diagram here, which illustrates the two lowest states of the hydrogen atom. You have the different energy levels of the electrons surrounding. Hydrogen is the most abundant element in the universe, and aliens surely would have interacted with hydrogen and know all about it. So these two states here is not the electron going from the one state to the two state. It's actually going from a spin down state to a spin up state. Now, electrons don't physically spin, but they do have angular momentum as if they do spin, and so we call it spinning. And so we denote that with a down arrow and an up arrow, and that's all quantum mechanics beyond the scope of this lesson. But basically, this diagram is telling the aliens, hey, everything on this diagram is going to be in terms of the time scale for this first transition of electrons in hydrogen, which hopefully you know all about, which was something about 0.7 nanoseconds in period. In other words, the light that comes out of this transition has a time scale of about 0.7 nanoseconds, and this is the fundamental time scale for everything on this drawing. Now I'd like to turn your attention to the upper left. You have an overhead view of a stylus which is resting on the surface of the record. So it's trying to convey to them that you have to play this thing from the outside in. That's how you read the data. Now you have to know how fast to turn the record to even read the data off, and it's all in terms of that hydrogen transition of 0.7 nanoseconds. Now if you look around the edge of this record, you'll see these vertical lines and also these dashed lines. And so the vertical line is a binary 1 and the horizontal dash line is a binary 0. So this is binary code. So with the ones and zeros illustrated as vertical lines and horizontal lines, we can convey a binary number that's hopefully very fundamental to anybody reading it. But the number that you get out of this in binary is in terms of the fundamental time of 0.7 nanoseconds. So you can get a number out of that, but it's that time, 0.7 nanoseconds. And when you do all the math here, what basically is telling you is the rotation rate of this record. Now directly underneath this overhead view is a side view showing the record rotating from a side view with the stylus resting at the edge. And you can also see a binary code underneath. And when you decode that binary code of ones and zeros, again in terms of 0.7 nanoseconds, what you get is a calculated runtime or playtime of the entire record, which is about an hour. So the first two diagrams is literally telling them how to read the data, how fast to spin the record, and how long it should take to read everything off of the record. And now next that we have all of this information that they read off of the record, we have to tell them how to handle it and what to actually do with it. All right, now you may or may not know that the old TV sets, the one that had the electron beam, the tubes, they had horizontal lines to paint the picture. But on the Voyager record, everything was in terms of vertical lines, vertical scan lines. So the way that you would assemble the picture is reading the data off the record and reassembling what you got into vertical lines, literally painted. Now there's no digital representation here. We're using ones and zeros to tell them how fast to spin the record, but this is an analog record. Just like we could play records before computers because everything was analog on there, it's the same way here. So all we're doing in the first diagram is we're telling them first of all that we're reading vertical lines. That's what the first part is. And then the waveform there, 1, 2, and 3, is telling them that it's the first line that you're painting down, the second line that you're painting down, and the third line that you're painting down. And the different waveforms here is telling you the intensity of the image that you should get as you read down that bit of data. And it's also telling them that as you read off the record, 8 milliseconds is about the length of time that one of these vertical lines on the picture will be. And how do they know it's 8 milliseconds? Because it's all encoded in binary underneath the waveform and everything's in terms of that transition of hydrogen there, 0.7 nanoseconds. So if they can read binary and they know about hydrogen, they know roughly how long each vertical line is represented on the record. That's what it's telling them. It's 3 different lines painted on here. Now underneath that with the sawtooth up and down, that's telling them that you take that data and you paint it down and then you go up to the next line and then you paint it down again and you go up to the next line and you paint it down again. That's what that is telling you there. And the triggering is every 8 milliseconds. That's basically what it is. Now the next diagram under that is telling them that to assemble an entire picture, it's 512 of these vertical lines. So we know how many milliseconds of data to read off the record is a single line, and we know to stack 512 of them horizontally, well, vertical lines, but stacked horizontally in order to make an image. And then finally, that image below with a circle in the middle, that is the very first image that's actually on and encoded on the golden record. So it's telling them, hey, if you decode it this way, and if you assemble 512 vertical lines of a certain length and time read off of this, all off of this analog record, then what you should get is a circle. Now let me tell you, the people that did this is very clever. Why do you think they picked a circle? Why couldn't the first image be, a duck or something? Well, it's because the people that reading the record, they don't know what they're supposed to be looking at. So it's telling them that this first picture is a circle. And the reason it was a circle is because they could then see that the aspect ratio, the ratio of horizontal to vertical width, is correct, because a circle is not going to be flattened like an ellipse. It's going to be that perfect circle shape, which again, we assume that any intelligent species knows all about circles. That's the first picture on there if you're decoding it correctly. Now this part here gives me chills actually. The decoding of the images is really cool, and it's all the human condition and all that. But on the lower left-hand corner, it looks like these lines coming out from a central point. Well, the central point of all these lines is supposed to represent Earth, the origin point of this spacecraft, right? Each of these lines represents the distance and the direction, relatively speaking, to a pulsar. A pulsar is what we talked about, a spinning neutron star, and so they pulse. You can see the flashes of the radiation coming off of these stars. They're very, very, very regular. Now, the distance of the line, the length of the line, is supposed to represent how far these pulsars are from Earth, which is in the center of the diagram. And if you look very, very closely at the diagram, you'll see that there's dashes, there's binary code and dashes and dots along the line. That is encoding how fast the pulsars are pulsing. Again, in terms of, on this record, the transition of hydrogen, 0.7 nanoseconds. So we can see the pulsars out there. We know how fast they're pulsing. So we've encoded not only how far away they are from Earth, but how fast they are pulsing. The idea being that if aliens know all about pulsars, and they know how they're pulsing, they can backward triangulate where the Earth is from knowing where all of these pulsars are in the galaxy. Now notice, along the center, the horizontal line is flat, and there's no dots or dashes, there's no binary code there, because that is the distance to the center of our galaxy. So it's telling them the distance and direction of the pulsars and the distance and direction of the center of the galaxy there from us. So hopefully from all of that information, they can kind of piece together what star system humanity is from. Now here's the part that is crazy, that the people that built this spacecraft thought of this. These pulsars, as we already know from our astronomy, we know that the rate of the pulsing changes over time. If you go 500 million years in the future, all the pulsars in our sky will still be pulsing, most of them will, but they'll be at a different rate than they are today because, you know, things wind down over time. Right? So what happens if an alien finds this 1 billion years from now? Well, what they did is they put onto this thing, and electroplated onto it on the surface, is a 2-centimeter diameter sample of uranium-238. Now get this, uranium-238 is radioactive, but it has a much larger, longer half-life. 4.51 billion year half-life. So it means it decays, but very, very slowly. So if an alien found this, they would certainly find the uranium-238 sample that was right on the record, right? And what they know is they're going to know that it was a radioactive sample. They're going to see the uranium-238 that's left over there, but they're also going to see the daughter products that the uranium has decayed into. So they're going to see uranium-238, and then they're going to see the daughter products, and they're going to know that some of that uranium-238 already decayed into these daughter products. And by knowing how much uranium-238 is there right now, and how much of the daughter products are there right now, and knowing the half-life of 4.5 billion years, they will be able to determine how long ago we launched the spaceship. Right? And so by knowing we launched the spaceship 1 billion years ago, let's say, then they'll be able to look at the pulsar map and say, okay, this is how everything was pulsing in the pulsars this many years ago. And they'll look into the sky and they'll be able to determine, hopefully, what pulsars we were talking about, because they're all going to be pulsing a different rate than they were when we launched the spaceship. So knowing the relative position of everything and how long ago it's launched, they hopefully will be able to figure out where we live. Now, I know we've all watched a lot of alien movies. Let's just hope that these are very friendly aliens. Now, as I wind down this video, I want you to know that before the Voyager spacecraft, humanity actually sent another message to the stars, and that was aboard the space probes Pioneer 10 and Pioneer 11. Now, these were not nearly as sophisticated as the Voyagers, but they were launched in 1972 and 1973, and these spacecraft actually carried aluminum plaques on board with similar but simpler messages etched on the surface. So the Pioneer plaque actually shows a picture or a drawing of a man and a woman drawn at scale next to the spacecraft, so they would have an idea of what humans actually look like. Now above that image is the same hydrogen transition diagram used on the Voyager record as a universal timescale, so to speak, and there was a similar pulsar map that shows the Earth's location, while a diagram of our solar system shows the Pioneer's trajectory as it left the solar system. So they reused elements of the Pioneer 10 and 11 plaques on the Voyager golden record, which was much more sophisticated with more information. Now, Pioneer 10 is actually heading towards the constellation Taurus, and it'll pass near a star called Aldebaran in about 2 million years. Now, Pioneer 11 is traveling towards the constellation Aquila, although it isn't expected to pass near any star for several million years. Now, let's get a little philosophical here. Just think with me for a moment. These 4 products of the human imagination, of the creation of human hands, Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11. They've escaped the gravitational well of the sun, and they will forever sail among the stars until someone finds them. Now, I have eternal hope that humanity will solve our own problems, but even if we solve every problem that humanity has, eventually the sun will swell in size and it will make the Earth uninhabitable. That's probably another video for another day. So hopefully humanity's figured out how to leave the Earth and go settle either other planets in our solar system or hopefully other stars in our galaxy. But even if we don't, it comforts me to know that there's a record of who we were somewhere out there that hopefully somebody or something can find. So returning to our hopefully friendly aliens who found this spacecraft, as they decode the golden record's contents, they began to understand. They began to understand what they actually found. That this was more than just a scientific space probe, more than just science. It was a bottle metaphorically thrown into the cosmic ocean by a very young civilization, just taking the earliest steps, reaching out towards the stars. They filled this bottle, so to speak, with their music. They filled it with images of who they were, their hopes and their dreams, quite literally. And now, after drifting between the stars for thousands or even maybe millions of years, someone had finally found their message. And as I said before, I just hope they're friendly because they have a map to know where we live. And as I close here, I'd just like to say that I don't know about you, but this gives me a little bit of hope, right? That no matter what, there will always be a part of humanity out there among the stars. I'm Jason. I'd like to thank you for hanging out with me as you gaze upon the stars. Try to think about the depths of the inky blackness out there. Imagine the Voyager spacecraft, maybe even the Pioneer spacecraft. They're speeding away at something on the order of 17 kilometers per second. Silent, dark, just running in between the stars. And I'd like you, as you think about that next time you look up at the stars, to always remember to stay curious. Learn anything at mathandscience.com.